So this is model question number 5, and in this question we will divide this question into three parts and we'll analyze every part. This is the first part. So basically this problem is a particle attached to the of midpoint of an elastic string. Right, so the natural length of elastic string is 2L. Elastic modulus lambda is taken as mg. And for any extension, you can find the uh, tension of the string based on this formula. So now the particle is attached to the midpoint. Since the natural length is 2L, and this string, the ends of the string is attached to fixed points A and B. I couldn't mention it here, but in the diagram you can see that the ends of the string is attached to these 2 points A and B. So the natural length is 2L. Since it is attached to the midpoint, that means this length is L and this length is L. So this is the particle is at rest now. It is under equilibrium at point O. Now, first part is to show that the motion is simple harmonic and find omega and t. You know what omega is? Omega is the angular velocity and t. Right. So, to show that the motion is simple harmonic, we're gonna sketch a general point here when the particle is under tension. So what I do here is that I'm gonna stretch it by a small amount of x. So you notice here that this string I've used a different color for this string. So when this is stretched, what happens is that this part will not be under tension. This part becomes slack, right? This part becomes slack, and this part will be under tension. So you can use F equal ma. Now since this is x, so x double dot in this direction, right? So F equal ma. Then tension acts in the opposite direction equal m x double dot. Mg and r is not influencing this motion in this direction. F equal ma. T becomes then minus lambda. Lambda is equal to mg. So let me just write mg here. Then x divided by L. Because now this is the natural length of this part. Natural length of this part is L now. Right. So mx double dot, m cancels out, and finally we are left with x double dot is equal to minus g over L x. So you can rewrite it like this: square root of g by L. So if we compare this with the characteristic equation, you know that omega squared is equal to, or let me just write omega is equal to root g over L. So we have figured out omega. Motion and let me write another thing. Find the center. So this is very important, right? The center is very important, especially when it comes to calculating time. Right. So we have shown that the motion is simple harmonic. Then the period time is t equals 2 pi o omega, which is equal to L over g, root L over g times 2 pi. Root L over g times 2 pi. Right. So that's about it for part A. So we'll meet again with part B.